that cycle, I showed you before I discussed the that might apply to cyclohexane or benzene, or maybe just 6-methane. But the connections between the carbons would be the same. But it's natural to associate that cycle with benzene. We did it. Right now, then, as progressed to benzene,
how do you account, excuse me, John?
Yes.
The question, just as a follow-up on this question. You had chlorobenzene.
Yes.
Only one item.
Yes.
You had chlorocyclohexane.
Well, where I was using the symmetry properties, that applies to benzene specifically. Because the symmetry properties of cyclohexane are obviously different from the symmetry properties of benzene. Right, so I showed you the diagram there for benzene with 6 carbons and 6 hydrogens, and it's the symmetry properties of that we use to calculate the number of isomers. So right now we have this maplet, so-called, and we can ask what is the number of isomers of a particular acyclic alkane. So let's start with ethane, and 1, right? And propane, 1. Butane, C4, 2. Pentane, 3. Hexane, 5. Anybody know the number of heptanes that we have? Oh, that's all right, here we go. There are 9 together, and so there are 8 shown there. There's another one. Now, this is the first case that we have asymmetric centers. Right, so if we consider this one, we see that this carbon has a methyl group, an ethyl group, and a propyl. Right, or 2-methyl. So this is an asymmetric carbon. So we have 2 optical isomers for this constitutional isomer. And then if we go up to octane, we have something new again. Find it. First of all, we have 18 isomers. So there are 8. There are 8 more. And there are 2 more. And one of these is, I think, meso compounds. So, like mesotartaric acids that Pasteur was interested in. Not that one. It's not one of these. Anyway, this just works for this is designed to work for the acyclic hydrocarbons. We have a table of results here. So if we have this number of carbon atomic centers, from 1 to 16, then we have this number of acarbon isomers, and this number of chiral isomers. So for heptane, we have 2 pairs, right, that's 4. And then for this number, we have this number of steric isomers, and this number of constitutional isomers. 10,359. That's what I calculated for C16. Right, well that's interesting, but I have tried it for IISER C20H42, but there's some organic, technical organic chemistry that claims that there are 366,319 constitutional isomers. Now let's go to general isomers and hydrocarbons. procedure for that, made by Alan Bickoff. And we can start with pentane again. And you see here is depictions. These are graphs. Right? And that's, to associate these graphs with the structures of molecules, we have to understand that the hydrogens are suppressed. So this is pentane, this is 2-methylbutane, this is 2,2-dimethylpropionate. Well, we saw that before. So now let's go to C5H10. And how many do we have in that case? Oh, we have 10 isomers. Let's have a look. What do we have? Yes. So we have cyclopentane, cyclobutane with a methyl group, cyclopropane with an ethyl group, or cyclopropane with 2 methyl groups. We also have this. Now this 2 here, that is the weight of that edge, and that means the double bond. Right? So now we are considering the possibility of weighted graphs. The weight corresponds to a single or double or triple bond. We don't bother putting a 1 on double bonds, but we begin with 2 here on the double bond. So this is pentene 2, this is pentene 1, this is butene 2, 2-methyl-2-butene 2. We have 2-methyl-butene 2. Right, so we can do that. Let's go to C3H4. And we have 3 graphs there. So this is cyclopropene, 1 double bond. This is propyne, 1 triple bond. Right? And this is propadiene, or alan, 2 double bonds, cumulative double bonds. Now, how is maple finding it? It's using permutations. It's calculating the permutations given that each carbon can have a maximum of, it has 4 valences, and 1, 2, 3, or 4 of those can be connections to other vertices. So if there is 1 connection to another vertex, then we assume that there are 3 hydrogens attached to that carbon. So let's see for C4H4. There are 11 structures, constitution isomers, and here they are. Now, when we look at these, we see that some of them are chemically feasible. They're all mathematically feasible according to the graph. But some of them are not chemically feasible, as any student of organic chemistry will recognize. So you can't have a double bond across the ring here. And you can't have a triple bond in the organic ring. You can't have 2 double bonds in this ring. But this might represent tetrahedrine, which is stable if you put methyl groups on there. This is cyclobutadiene, and that is stabilized when it's a ligand, methyl atom. This is what? This is butatriene. That's stable. And this is butene-9. So binon is secondary. This is stable. But the others are not chemically stable. Well, what about C6H6? C6H6. How many structural isomers can we imagine? Which one is benzene? Do you have any idea?
217.
217? 17? Aha. Let's see what Maple says. 220. Now there's a noted organic chemist in Japanese electron optics company, NMR spectrometer, and they showed diagrams of these 217 isomers. I find 220, and I believe me, but I haven't looked at them. It would take some time to compare the diagrams. The diagrams can be generated here, and this all this material is available as chapter 11 of my book, so we can download that from the site, the website at CTCM, sfu.ca, and you can run it provided you have paper for the book. It's free, right? But you have to have paper to run it. And if you're interested to see whether paper was right or Alexander Balaban was correct, right? Well, you can do that all the time. As I mentioned, we use the symmetry properties here to prevent recycling propane, but Maple just uses the permutations. Now, in chapter 10 on group theory, I have derived 32 crystallographic point groups by 3 methods. By symmetry operations, by permutations, by generators and relations. So if you look at chapter 10, you can find that the derivations for those things with much of the material of the mathematical side of group theory. Well, I talked long enough. Thank you for your attention. I hope it has been interesting. I'm not too technical. All the technical detail is available in the book, and you can consult that at your leisure. Thank you.
Are there any questions?
So, is this method applicable for other electronic containing compounds like oxide?
Yes. All you have to do is change the
Electronic is there now.
you see, all this is done assuming that the carbons are indistinguishable. If you have oxygen or nitrogen, then you have to distinguish that from the others. And that means a slight change in the percentage data. And also the fact the oxygen would be only 2, air is 2, and nitrogen 3. All they can be done. I haven't done it. I've just done this for illustrative purposes.